Okay, yeah. Welcome back, everyone. It's my great pleasure to introduce Alberto Raffaello from University of Torino, who will speak to us about homogeneous fixed points of the generalized Ricci flow. So please, Alberto.
Okay, thank you, and many thanks for the introduction and also for the kind invitation. So in this talk, I'm going to discuss some special solutions to the generalized Ricci flow, which are the fixed points. And I will consider the case where they are homogeneous, so where there exists a transitive group of automorphisms of these fixed points. And what I'm going to talk about today is based on a joint collaboration with Fabio Podestà from Università di Firenze. And if you're interested in the details, you can find more details in these two papers on the archive. So let's start. So today I will focus on fixed points of the generalized Ricci flow. That admit a transitive automorphism group. So this will be the focus today. And so let me recall some basics on these objects. And so let's start from the definition of the generalized Ricci flow. So the setting will be a compact Riemannian-oriented Riemannian manifold. And on such a manifold, I will fix a closed free form so that its exterior differential is 0. And then the generalized Ricci flow that I will shorten with, as usual, with GRF for a family of metrics depending on the time, and for a family of 3 forms that are just given as this one here, so that evolve in the cohomology class of the closed 3 form we have fixed, is given by the following evolution equations. So the metric G evolves in the direction of minus twice the Ricci tensor of G plus 1/2 asymmetric to tensor H2T that I shall define in a while. And the 2 form BT evolves in the direction of minus the codifferential of HT. For here, so this H2 here, I recall is a symmetric to tensor defined on every pair of vector fields X and Y as the product of the contraction of H with X and the contraction of H with Y. And this is a symmetric to tensor. So in particular, we have some kind of perturbation of the usual Ricci flow equation here. So what are the fixed points of this equation? Are pairs, let's say GH, given by a Riemannian metric on the manifold and a closed 3 form H, such that the Ricci tensor of G equals 1/4 the symmetric to tensor H2, and the codifferential of H is equal to 0. And so in particular, what we have is that H is a harmonic 3 form. Now, so these are the objects I'm interested in today. And let me recall that once we have such type of object, so such a pair, we can define, starting from it, a connection which is metric and has totally schizometric torsion, which is defined as the Levi-Civita connection of the Riemannian metric G plus 1/2 the 2-1 tensor that one obtains by raising one index of H using the metric. So this is a metric connection with totally schizometric torsion, which is given by the free form H. And this is what in the book by Stritz and Garcia Fernandez is called the bismuth connection induced by the pair GH, as it has as a special case the usual bismuth connection in the case of Kähler with torsion matrix in complex non-Kähler geometry. So in such a case, once we consider this metric connection here, then since it has non-trivial torsion, its Ricci tensor is not symmetric, and in particular, it will split as follows. You will have a symmetric part, which is given by the Ricci tensor of the Riemannian metric minus 1/4, the symmetric to tensor H2, minus 1/2 of the codifferential of H. So we have the splitting in the symmetric and skew-symmetric part. And thus, from this, you can see that we have that GH, the pair, is a fixed point of the generalized Ricci flow, and so it satisfies this system here, if and only if the Ricci tensor of the corresponding bismuth connection is 0. And so if the corresponding bismuth connection is Ricci flat. And to shorten everything here, I will use this definition that we used in the paper with Fabio, and I shall call a pair GH given by a Riemannian metric G and a closed three-form H, a bismuth Ricci flat pair, and I will shorten it with BRF if the Ricci tensor of the corresponding bismuth connection is 0, which is equivalent, let me recall it once more, to having the Ricci tensor of G of the Riemannian metric equal 1/4 of the symmetric to tensor H2, and let's say the Laplacian of H equal to 0. So if one is interested in looking for solutions of such an equation on a given manifold, one has to find a Riemannian metric whose Ricci tensor satisfies this first equation, and a three-form that is harmonic with respect to the Hodge Laplacian induced by that metric. So in this sense, we have a coupled problem here. And there are some useful constraints that one can use that are imposed by the problem. So if one is interested in looking for solutions of this problem here, and so in finding bismuth-Ricci flat pairs on a given compact manifold, then we know that if the pair GH is a bismuth-Ricci flat pair, then, well, for sure, on a compact manifold, we must have the third-Betti number of the manifold greater than 0. And this is because H is a non-trivial harmonic three-form. And moreover, if we trace this first equation here, we will get something like the scalar curvature of the Riemannian metric G equal 1/4 the square norm of H, and this has to be constant. And as far as I know, this was first proved by Quan-Hui Li in a recent paper that appeared at the beginning of 2022 on the archive. And so in particular, this last condition here suggests that the homogeneous setting is a good setting where one may try to look for examples. So in the homogeneous setting, one is considering a manifold with a pair like this one here, and assumes that there exists a group of diffeomorphisms of the manifold that preserve both G and H by pullback. There are some known examples in the literature.
Alberto, I have a question.
Yeah.
So I don't understand the condition on the third-Betti number. So it's not possible that the cohomology class of H is trivial?
No, because if you would like to have a non-trivial harmonic threefold, and the point is that since the manifold is compact, you can use Hodge's theorem to conclude that you need a non-trivial harmonic representative of the cohomology class.
Sure. Yeah. Thanks.
Okay, so there are some examples in the homogeneous setting which are in some sense trivial, but let me recall this because I will need that later. So let's start with G, a compact semi-simple Lie group. And on such a Lie group, we can always consider its Cartan-Killing form that I recall is defined from the algebra of G times itself to R, and on a pair of left invariant vector fields is given by the trace of the composition of the joint maps at the algebra level. And this is negative definite since we have a compact semi-simple group, and it is invariant under the action of the joint representation. And so this tells you that if you consider it's negative, then it will induce a bi-invariant Riemannian metric on the Lie group. And this follows from the G invariance of the Cartan-Killing form at the algebra level. So once we have this, so we have a Riemannian metric on the Lie group, which is bi-invariant, and we can use this metric here together with the bracket to construct a threefold that I shall denote by H capital G, that on a triple of left invariant vector fields X, Y, and Z is defined as the scalar the product between the bracket of X and Y and Z, or X, Y, and Z left invariant. And it is possible to show that this is a bi-invariant harmonic threefold on the Lie group G. So once we have such a pair given by this metric G and this harmonic threeform H, we get two bismuth connections on the manifold, so on the Lie group G. If we consider the pair given by G capital G, H capital G, then this will induce a bismuth connection that is usually denoted by nabla plus, that on a pair of left invariant vector fields X and Y is just the bracket of X and Y. And if you consider the pair given by the same Riemannian metric, but H with the opposite sign, then you will get another bismuth connection that is just equal to 0 for each pair of left invariant vector fields X and Y. And these connections here are flat. And this is obvious in the second case. And in the first case, it follows from the Jacobi identity for the Lie bracket once one computes the curvature tensor of such a connection. So they are flat, and thus, in particular, they are bismuth-Ricci flat. So they are BRF according to the definition I said before, but of course, trivially, because the whole curvature tensor here is 0.
Can I ask something?
Yeah.
So which proof do they give of the scalar curvature being constant?
It's more or less you play a little bit with the covariant derivatives, like in the case where you show that the scalar curvature has to be constant for an Einstein metric when the dimension of the manifold is greater or equal than 3.
Yeah, I mean, there is a very simple proof which is implicitly contained in the book, which is you take covariant derivative covariant derivative and trace of the symmetric part of the Ricci, of the generalized Ricci tensor, and then you get that the generalized scalar curvature is constant, but also the trace of the generalized Ricci is constant, and then you subtract, and you get that both the scalar curvature and the normal page square are constant. So it's pretty.
Okay.
Yes.
So I missed that on the book. Sorry. Thank you for pointing it out. Okay. So we have such an example that, in some sense, is a Bismuth-Ricci flat pair, but it's trivial since it comes from a flat pair. But in any case, so we have that this metric G and plus minus HG are, let's say, trivial Bismuth-Ricci flat pairs, and the data given by the Lie group G, the bi-invariant metric G, capital G, and the three forms plus or minus HG is an example of G homogeneous space with such a pair. So we have such an example, which is trivial in this sense, since it comes from something that is flat. And actually, it is possible to show that if one has a complete simply connected manifold, Riemannian manifold with a closed reform H, such that the Bismuth connection induced by the pair given by the metric and that closed reform is flat, then the manifold is isometric to a semi-simple Lie group with a bi-invariant metric and torsion form given by the bracket with up to a sign. And this is a result that goes back to Cartan-Schouten. So on the other hand, from, let's say, Cartan-Schouten 1926, and also more recently with a different kind of proof in a paper by Agricola and Friedrich, one has a kind of characterization of which are the possible Bismuth-Ricci flat, complete simply connected manifolds that admit flat metric connection with totally symmetric torsion. And which is the idea here is that if we have a manifold that is a Riemannian product of two manifolds, let's say M1 and M2, with a product metric, and we have H closed tree form on the manifold M, such that the Bismuth connection nabla given by nabla G plus 1/2 G to the minus 1 H is flat, then what happens is that essentially the connection splits and the torsion splits. So H splits as the sum of two forms, one on M1 and the other one on M2, and also the Riemannian manifold with the connection with totally symmetric torsion splits as a product. So let's say M1 G1 nabla 1 cross M2 G2 nabla 2. So in particular, as a consequence of this, when the manifold M is complete and simply connected, we can consider its the RAM decomposition and focus on the reducible pieces of this decomposition. And under such an assumption, what one can show, and this is the theorem by Cartan and Schouten, is that if you have a complete simply connected and irreducible manifold, and if we assume also that H is closed and the bismuth connection induced by the pair GH is flat, then the Riemannian manifold Mg must be isometric to a compact, simple D group with a bi-invariant metric and the torsion that is just given by plus or minus the bracket of X and Y on left invariant vector fields. And let me remark that if you drop the assumption that H is closed, then in such a case, also the seventh sphere occurs. So this tells one what's going on for flat bismuth connections in the complete and simply connected case. So essentially we have, if the three-form H is closed, we essentially have semi-simple groups with bi-invariant matrix and torsions given in this form here. And so the problem now is to understand whether there exists homogeneous non-flat examples. And if you think about this problem here, similar problem in the Riemannian setting, then we know the answer. And this is given by a theorem by Alexievsky and Kimmelfeld, who proved that if we have a homogeneous Riemannian manifold such that the Ricci tensor of the metric is 0, then the metric and the manifold is actually flat. So this was proved by Alexievsky and Kimmelfeld in 1975. And so here, inspired by this result here, one can ask, in particular in the setting we are interested in today, the following question that was posed in the book by Garcia Fernandez and Streets, and reads as follows. So given a homogeneous Riemannian manifold with an invariant 3,4 H such that the bismuth connection induced by the pair GH as 0 Ricci tensor, then is the connection necessarily flat? So this was the starting point of the collaboration with Fabio Podestà. So we focused on this problem here. And let me say that the answer to this question in the three-dimensional and the four-dimensional case is well understood. So these two cases are well understood from the work of Garcia Fernandez and Streets, and in particular from the results you can find in the book on the generalized Ricci flow. And in fact, what we have are the following results. So in dimension 3, if M is a three-dimensional manifold with a pair GH such that the Ricci tensor of the bismuth connection induced by GH is 0, then H must be proportional to the volume form of the Riemannian metric G for some real constant lambda, and the Riemannian manifold MG must be isometric to a space form, and in particular, it has zero sectional curvature if lambda is 0, and positive sectional curvature if lambda is positive. Otherwise, let's say. And in particular, in such examples here, we have that G is Einstein and that nabla is flat. In the 4-dimensional case, it follows from an argument they use to prove a result in the book, that if you consider a compact 4-dimensional Riemannian manifold with a pair GH such that the corresponding Bismuth connection is Ricci flat, then the connection is actually flat. And so let's say that in 3 and 4 dimensions, we know the answer to this question. And so the first interesting dimension where one can investigate the existence of compact homogeneous spaces admitting a non-trivial BRF pair is the 5-dimensional case. And in such a case, with Fabio Podestà, we got a complete answer to the problem. So let me record the result here. So if we have a compact G homogeneous Riemannian manifold with H and invariant closed 3-4, such that the Ricci tensor of the Bismuth connection induced by the pair given by G and H is 0, then two possibilities occur. Either M is finitely covered by a compact D group, or M is finitely covered by the 5-dimensional manifold homogeneous space given by SU2 cross SU2 over a 1-dimensional torus diagonally embedded into it. And this is just, let's say, some necessary conditions. So if we have all of these hypotheses here, in particular for any D group, so we are not assuming G to be necessarily semi-simple here, then necessarily one of these two possibilities has to occur. But this doesn't say that, this is not saying that you have non-trivial Bismuth-Ricci flat pairs on this basis. This is another type of problem. And as far as I know, the only examples of Bismuth-Ricci flat pairs on compact D groups that are homogeneous are those I mentioned before. So those coming from, which are actually flat. So I do not know whether on a compact D group there exists a left invariant Bismuth-Ricci flat pair that is not flat. In the second case, one can investigate what's going on and actually find solutions which are Bismuth-Ricci flat and non-flat.
I'm sorry, Alberto.
And yeah.
Just so I understand, yeah, so like this statement is topological. You're saying these are the only possible topologies?
Yeah.
Okay.
Yeah, these are the only possible ones. And then you have to, of course, in the first case, I do not know whether there are other examples besides those I mentioned before. In the second case, one has to look for examples, whether they exist or not. And this is what we did in the second part of the proof of this theorem. And so in the second case, what we have is the following. So let me denote by G the Lie group SU2, and this one-dimensional torus diagonally embedded into SU2 cross SU2 can be taken to be isomorphic to such a space here that I shall denote by KPQ, which is just given by pairs of matrices of the following form. So we have ZP 00Z to the minus P and ZQ 00Z to the minus Q belonging to G cross G, so to SU2 cross SU2, such that Z belongs to T1, so to the one-dimensional torus. And up to an inner automorphism of SU2 cross SU2, you can always assume T1 to be of this form here for P and Q positive integers with P greater than or equal to Q greater than or equal to 1 and coprime. So once we have this, we get homogeneous spaces that we denoted by MPQ, which are given by G cross G over KPQ, where G again is SU2, and KPQ is a one-dimensional torus embedded diagonally into this product here. And from the topological point of view, these spaces are all diffeomorphic to S3 cross S2, and this was shown by one Ziller, even if there is no explicit diffeomorphism. So it is another type of discussion to show this. And they are principal S1 bundles over SU2 cross SU2 over T2, which is isomorphic to the product of S2 with itself. So we have these spaces here, and so once you have this presentation here, you can work out which are, you can consider a reductive decomposition of the algebra of the group G cross G and identify the tangent space to the manifold at a fixed point to the complement of the algebra of the isotropy and work at the algebra level. And so reduce the existence problem of Bismuth-Ricci flat pairs to a kind of algebraic problem on the tangent space of a fixed point of the manifold. And it is possible to solve this problem. And actually, what we showed is that all of these spaces, MPQ, admit a G invariant non-flat Bismuth-Ricci flat pair GH, and moreover, we were able to describe, at least locally, which is the moduli space, the moduli space of the solutions. And in particular, if P is different from Q, then this solution is essentially unique up to scaling. So the space of all G cross G invariant BRF pairs is given by one fixed pair up to multiples. So it's just scaling of the pair we have. And this is easier because when P is different from Q, the spaces of invariant tree form are smaller. So the dimension of these spaces is smaller compared with the case where P is equal to Q and equal to 1. So if P is equal to Q and equal to 1, one gets, let's say, an algebraic problem that is more difficult to solve if compared with the case where P is different from Q. But in any case, one can find solutions and also show that locally in a suitable neighborhood of the solution we have, the only other possible solutions are those that are obtained by scaling the solution we are considering. So in particular, in such a case, what happens is that there exists a neighborhood of the solution GH, let's say U, in the space of matrix times closed three forms on this manifold M11, such that if you consider the intersection of this open neighborhood here with, let's say, the space of left invariant Bismuth-Ricci flat pairs on this manifold M11, then this equals U intersected with R plus acting on the solution GH we got. So in this sense, this solution is locally unique up to multiples. We do not know in such a case whether there are more solutions because the equations you obtain in the second case, so when P is equal to Q is equal to 1, are more complicated compared with the equations you obtain in the first case. But in any case, this answers the question posed before negatively. And in particular, we obtain examples that are homogeneous, compact, Bismuth-Ricci flat, and non-flat. Let me add some remark on such examples. So first of all, the metric G in these examples is not Einstein. And moreover, the torsion tree form is not parallel with respect to the Bismuth connection. And moreover, if one would like to relax a little bit the hypothesis in this question here, and so not focusing on closed tree forms, but any invariant tree form, then one can also obtain solutions. So there exist, and it is not difficult to find them in the first case where P is different from Q, there exist G cross G invariant examples with H not closed and zero Ricci tensor for the Bismuth connection and non-zero curvature for the Bismuth connection.
Sorry, in the statement of the result, what is U?
Sorry, U is an open neighborhood. So it's a neighborhood of the solution you get. So you obtain an explicit solution in this case. So as I was saying, you have to solve a system of algebraic equations, and you find a solution that gives you a Bismuth-Ricci flat pair that is not flat. And then you can show that there exists a neighborhood U of this solution here in the space of matrix times closed tree forms, for which, if you consider the intersection of this neighborhood with the invariant Bismuth-Ricci flat pairs on this manifold, then you only have that pair up to multiples on that neighborhood. So this tells you essentially that locally you only have this example of up to multiples.
Okay, thanks.
But sorry, while we're on it, I mean, it's not possible to make like a stronger uniqueness statement. Like you don't know if these are unique.
Yeah, the point is that here the equations you have are really more involved. So we're not able to deal with them in that sense. So.
Yes. But you do have in P not equal to Q, I guess it's just unique, I suppose.
Sorry?
in the case P not equal to Q, I guess the claim is that it's just completely unique. I see.
Yeah, in that case, yeah. Yeah, the point is that the equations are too complicated in the second case to obtain a similar statement. So we were able to obtain that only locally. So we were not able to exclude the existence of other solutions that are not equivalent to this one. Okay. So once we are here, so we saw what's going on in the 5-dimensional case, which was the first available dimension after the 3- and 4-dimensional cases where the question was well understood. What we can ask is whether these examples here are just some, let's say, special examples or whether there exist more examples. So now the problem becomes other higher dimensional examples. And in particular, even dimensional examples, if one is interested also in the even dimensional case. And in fact, it turns out that it is possible to show that this example here, actually not all of these examples, but the second one where P is equal to Q is equal to 1, is a special case of a more general construction. And this is the second theorem I would like to mention today. And the general construction is the following. So we consider the following data. We start with G, a compact, connected, semi-simple Lie group. And we consider sigma from G to G an involutive inner automorphism. So this means that sigma is the conjugation by some element Z in G. And so let's say that tau Z acting on some element H in G is just the conjugation by Z. And sigma squares to the identity. So this is inner and this is the involutive condition. So starting with this data here, then we have what follows. So first, if K inside G is a compact subgroup such that it is contained between the identity component of the fixed point set of the involutive inner automorphism sigma and the fixed point set, which is just the set of points in G, which are fixed by sigma, then the space, the manifold M given by G cross G over K diagonally embedded into the product is endowed with an invariant non-flat Bismuth-Ricci flat pair. Let's say over line G, over line H. And moreover, in the case where K equals this fixed point set, what we have is that there exists a G cross G equivariant minimal embedding of M inside the product of G with itself, which is induced by the following map. going from G cross G to G cross G that sends a pair G1, G2 to G1, G2 to the minus 1, G1, Z, G2 to the minus 1, where this Z here is the point we fixed before, and such that the Bismuth-Ricci flat non-flat pair over line G over line H is just the pullback with respect to this embedding here of the Bismuth flat pair given by the sum of the bi-invariant Riemannian matrix on the product group G cross G and the sum of the harmonic tree forms capital HG that we mentioned that we considered before. So this is what one can show, and moreover we can say also something about the properties of this manifold M, which is defined in this way. And what we can show is that M has finite fundamental group and moreover its third Betti number equals the number of simple factors of the semi-simple Lie group G. In particular, as a consequence, if G is simple, then the third Betti number of the manifold is 1, and M cannot be diffeomorphic. To a product of lower dimensional manifolds carrying a Bismuth-Ricci flat pair with non-trivial tree form H. And in other case, so if G is semi-simple but not simple, let's say with L simple factors, then what's going on is that the manifold is finitely covered by the product of L factors of the form as we have here. So what's going on is that in such a case, the manifold is finitely covered by the product of L factors of the form, let's say G prime cross G prime over K prime diagonal with G prime simple and the pair G prime K prime as above in the statement. So with everything that is going on here as an assumption. So this is what is called in the literature an inner symmetric pair. And so this is the whole statement of the result. So we get more examples that include the 5-dimensional example I mentioned before. And
can you say again what is the hypothesis on the compact group? The first hypothesis you put it, can you say that?
Compact connected and semi-simple.
Yeah, no, yeah,
and
but
then, and then you assume that there exists an involutive inner automorphism.
Yeah, but the K is a compact group, says that what?
Yeah, it is contained between the fixed point set of this involutive automorphism and the identity component of the fixed point set.
Oh, okay.
So this tells you essentially that GK is a symmetric pair. So this is what's going on. So in fact, what we have is that in the assumptions, GK is a symmetric pair. And moreover, we know that the involution sigma is inner. So it is the conjugation by some element of G, if and only if the fixed point set of G has maximal rank. In G. And we have plenty of examples of pairs satisfying these properties here. Moreover, in this construction, we have always that H is not zero, so the overline H that we get, so the tree form that we get on the manifold N that induces the Bismuth-Ricci flat pair. And moreover, it is never parallel with respect to the Bismuth connection induced by the pair overline H overline G. And finally, we have that infinitely many examples occur from this construction. And in particular, let me just switch for a moment to this table here. So in particular, if we start with a symmetric pair of compact type with the algebra G that is simple, and the rank of this subalgebra K that is equal to the rank of G, then we get an example that, as I said before, since the group is simple, has third Betti number equal to 1, and we obtain examples for all these choices of pairs G and K that I reported here. So you consider just the table of all Riemannian symmetric spaces, and you find out which are those pairs where the rank of the algebra G equals the rank of the isotropy subalgebra K. So in particular, if G is simple, you get examples that are irreducible as manifolds, and you can also compute the dimensions, and the first 128 examples, for instance, give you manifolds of the following dimensions. So we have the 5-dimensional case that is the one I mentioned before, but actually this is only M11, so this construction does not include also the MPQ with P different from Q. And then we also get many examples that are even dimensional and so on. So we get infinitely many examples, and let me just discuss now how the proof of this result works.
Sorry, you don't get anything in dimension 6 or 8?
No.
Okay.
So in dimension 8, you have something that splits. So it splits as 5 plus 3. So it's the 5-dimensional one plus the trivial one on the 3 dimensions.
Okay, thanks.
Okay, so which is the idea? So the idea is that, first of all, it is sufficient to focus on the second case where K is equal to the fixed point set of G as G cross G over K diagonally embedded is a finite covering of G cross G over G sigma diagonally embedded. So we focus directly on the second case here. So which is the action we are considering is the following. So we have that G cross G acts isometrically on G cross G endowed with the metric, let me denote it by G from now on, which is just the product metric of the bi-invariant matrix on the group, preserving the tree form H defined as the sum of the harmonic tree forms H, G, A, G under the group as follows. We have that G1, G2 acts on the pair X1, X2 as G1, X, G2 minus 1, G1, X2, G2 to the minus 1. So this is the action we are considering of G cross G on itself, which is isometric and preserves the harmonic tree form H defined in this way. Now we have sigma by hypothesis that is an inner involution. And so, as I said before, it is the conjugation by some element Z belonging to G. And the fixed point set of sigma in such a case, which is the set of points in G, which are fixed by sigma, is just the set of points in G which commute with Z. And so this is nothing but the centralizer of Z inside G. Now we fix the following point, P, which is given by the pair Ez in G cross G. And we consider its orbit. The orbit, as we know, can be represented as G cross G over the isotropy of the point P. And what's going on here is that the isotropy of the point P is given by pairs G1, G2 in G cross G, such that G1, G2 acting on Ez preserves it, so it's equal to Ez. And a computation shows that, just straightforward computation shows that this is just given by pairs AA, such that A belongs to the stabilized, to the fixed point set of sigma. And so this is precisely G sigma diagonally embedded inside G cross G. And so in particular, what we get is that G cross G acting on P, and so the orbit through P of this action of G cross G is isomorphic to G cross G over the isotropy at the point P, which is G cross G over G sigma diagonally embedded, which is precisely the manifold M we are considering in the statement. So this is how the manifold is realized inside G cross G. And so in particular, we have an embedding of M inside G cross G, and we can pull back the metric G, obtaining this metric that I denoted by overline G, and we can pull back the tree form H, obtaining this tree form overline H on M. And let me recall again, this is the product of the bi-invariant matrix on the product of the product G cross G, and this is the product of the harmonic tree forms, bi-invariant harmonic tree forms on G cross G. So you just put them back, and now you look what's going on the tangent space to the point we have fixed. So now you look what's going on at the algebra level. And what we have is the following. So first of all, if we just focus on the algebra of G, then we see that it will split orthogonally with respect to the Cartan-Killing form as the sum of two subspaces. C is the Lie algebra of the fixed point set of the involutive automorphism sigma. And this is just the set of vectors in G that are preserved by the action of at Z. And Q, which is its orthogonal complement with respect to the Cartan-Killing form, is described by the vectors in G such that at Z acting on U equals minus U. So it's the orthogonal complement. Let's see. So this is what's going on for the Lie group G at the Lie algebra level. If we consider now the manifold M with this presentation, what we have is that at the Lie algebra level, we have the sum of G with itself, the algebra of G with itself, and this splits as the algebra C diagonally embedded, which is the algebra of G sigma diagonally embedded inside G cross G, plus three summands, which are, let's denote them by P and 1 and 2. And these three summands here give the tangent space to the manifold M at the point, so they can be identified with the tangent space. So this is a reductive decomposition. And so in particular here, C diag is just given by pairs U and U, such that U belongs to the Lie algebra of the fixed point set of sigma. P is given by pairs of the form U minus U, such that again U belongs to the Lie algebra C. And M1 is given by pairs of the form V0, such that V belongs to the orthogonal complement Q of the Lie algebra C. And M2 is given by pairs of the form 0V, such that V belongs to Q. So this is the relative decomposition, and so you can work at the Lie algebra level now, working on this space here that is identified with the tangent space of the manifold at the point we fixed. And then we recall that the isomorphism between P plus M1 plus M2 and the tangent space to M at the point is obtained via the map sending a vector here to the vector field it induces at the manifold level evaluated at P, which is just the time derivative at time 0 of the exponential of TV applied to P. And the notation I will use is the following. So we have this correspondence. And so if I will consider vectors of this form here, I shall denote the corresponding spaces as P hat and 1 hat and M2 hat. So now we see what's going on with the metric G overlying G. And what we have is that the decomposition of the tangent space to the manifold at the point, which is given by P hat M1 hat, M2 hat is overline G orthogonal. So you can compute directly this. And moreover, you can see that if you pick V equal to U minus U and W equal to, let's say, V minus V inside P, then the inner product between V hat and W hat equals -8, the Cartan-Killing form evaluated at the pair UV. And on the other hand, if V is equal to V0 and W is equal to small w0 and they belong to the sum of them 1, or if V is equal to 0 small v and W is equal to 0 small w and they belong to the sum on M2, then the inner product of the corresponding vectors on the tangent space is given by minus twice the Cartan-Killing form of V and W. So you know what's going on for the metric on the tangent space of the fixed point you have chosen. And in particular, you can compute everything in terms of the Cartan-Killing form of vectors belonging to the decomposition of the Lie algebra G, of the Lie group G. So now, to proceed, you focus on the fact that M embeds inside G cross G, and thus, for, let's say, X and Y vector fields on M that are arbitrarily extended to the whole G cross G, you can split the bismuth connection on G cross G as follows. You get the bismuth connection on the manifold M induced by the pair overline G overline H, plus the second fundamental form of the immersion, plus a third summand, which is just the torsion evaluated at xy, transformed before doing this in a 2-1 tensor, orthogonal complement. And so once you have such a decomposition, you will end up with some Gauss-type formulas for the Kovato tensor and the Ricci tensor of the bismuth connection on G cross G, which involve the Kovato tensor, the Ricci tensor of the bismuth connection on the manifold M, the second fundamental form, and the mean curvature vector mu. And now, again, with a computation similar to the one we did before to see what's going on for the metric, one can show that the second fundamental form evaluated onto vectors that are tangent to the manifold at a point is different from 0 if and only if these two vectors come, one from the summand M1 and the other one from the summand M2. So in particular, if you trace this second fundamental form to get the mean curvature vector, you will obtain that it has to be equal to 0. And so in particular, the manifold is minimal inside, so this immersion is minimal. And finally, once you get this, you recall that nabla is flat. It is the flat bismuth connection on G cross G. The mean curvature is 0, and so the expression of the Ricci tensor of the bismuth connection induced by the pair overline G overline H on the manifold M simplifies and allows you to compute directly the expression and obtain that it is 0. And so now the problem is consisting showing that this pair over line G over line H, which is a BRF pair, according to the definition I gave before, is not trivial, so the connection is not flat. And again, this follows from the setting we are considering. We can always choose X and Y belonging to the orthogonal complement of the algebra of the fixed point set of the involutive automorphism sigma, such that their bracket that will belong to the algebra of the centralizer of G, so to the orthogonal complement of Q, since G sigma is a symmetric pair, is not 0. And we can always find such a pair, as otherwise what we will have is that the metric on the symmetric space we are considering is flat. And so this will give a contradiction. So we can always find such a pair. And so if we consider, let's say, capital X given by X0, capital Y given by Y0, belonging to M1, capital Z given by 0x, and capital W given by 0y, belonging to M2 in the decomposition of the tangent space at the point P, then a direct computation shows that the curvature of the bismuth connection nabla over line nabla at X hat, Y hat, Z hat, W hat is equal to -4 the square norm of the bracket of X and Y, and it is different from 0. And I checked also all other possibilities, and I think that this is the only possibility to having this different from 0. So I think that all other possible combinations of vectors in the other summands on which the tangent space at the point P decompose will give you a 0 component of the curvature tensor here. So these are Bismuth-Ricci flat pairs, these are not flat. And finally, you can show that over line H is not parallel using this result. So the previous result. So this one here, together with the fact that H is closed and some suitable identities.
That's right, Alberto.
Yeah.
I guess, so this curvature quantity you wrote down, I mean, these aren't sectional curvatures, I guess. And so the sectional curvature will probably be like mixed sign. It won't have a sign, I guess. Or is it right?
Well, actually, this is the only one different. So I guess this is the only. I didn't do the full computation, but I guess this is the only one different from 0.
Okay, thanks.
So I guess that if you will compute something, let's say on M1, 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 you will get 0. Something like that. Okay. And yeah, okay. And then just to conclude, yeah, almost out of time. So to conclude, and so to say what's going on for the geometry of M, the point here is that you can show that M is diffeomorphic to the product of G times G over G sigma as a smooth manifold. But this diffeomorphism is not an isometry if you endow M with the metric overlying G and you endow this product with the bi-invariant metric that I denoted by G capital G on the D group G and the standard metric you have on the symmetric space G over G sigma. So you just have this diffeomorphism, but then you can use known results by Borel to conclude that M as finite first fundamental group and that the third, so let's say the third cohomology group of M is isomorphic to the third cohomology group of the Lie group G. And so in particular, this tells you that the third Betti number of M equals the third Betti number of G. And so again, if G is simple, you will get that this one is equal to 1, and so the manifold won't split. Otherwise, you will show that the manifold splits up to a finite cover, as I said before in the statement. Okay, so maybe just conclude with one remark that is related to some observation we made last week at the end of the talk of last week, which was something about the existence of invariant complex structures when M is even dimensional. So here, what the feeling is that the existence of invariant complex structures of such spaces in the even dimensional case is highly unlikely. And the point is the following. So we haven't proved this, but what's going on here is that we have a manifold M, let's say given by G cross G over G sigma diagonally embedded, with finite fundamental group. And so if it admits an invariant complex structure J, then this is what is known in the literature as a C-space. And these spaces were studied by Wang in a paper published in 1954. So if such an invariant complex structure exists, M must be a C-space. And so we know from the results of Wang that such spaces have a precise characterization. And in general, given M equal G over K, a homogeneous space with G compact semi-simple, K closed connected subgroup of G by one finite and dimension of M that is even, then if M admits G invariant complex structures, then it must have the semi-simple part of the isotropy that is equal to the semi-simple part of the centralizer of some torus in G. And so in particular, among our examples, if one is interested in looking for invariant complex structures on these examples in the even dimensional case, then one has to look at this condition here. So one has to check whether it is possible that the isotropy, which is in our case G sigma diagonally embedded inside G cross G, can be described as the semisimple part of the centralizer of a torus inside the group G cross G. And we haven't done this, and of course we didn't have disproved this. But of course, if one is interested in looking for invariant complex structures, one has to see whether among all these infinite families of examples, there is one satisfying whose isotropy satisfies this condition here. And I do not know the answer to this question so far, but this leads to another interesting problem, in my opinion, that is the search for examples of the type I discussed today, so for BRF pairs on these C spaces. So what's going on next is the search for examples of BRF on C spaces. And this is a work in progress.
Can you remind what the definition of C space is?
Yeah, it's just a compact, complex homogeneous space with finite first fundamental group, which admits a transitive action of a real compactly group.
I see. Okay. Yeah. Okay. Thank you.
So if any of our examples admits an invariant complex structure, then it has to be a C space.
Mm-hmm.
And so this condition has to be fulfilled. Okay, so I think that I can conclude here. So thank you very much for your attention.
Yeah, thanks. Thank you, Alberto. Are there more questions?
So I have a comment.
Yeah.
I wonder if you can, if you can recover your result from generalized reduction. So there is this.
Oh.
So there is this. I don't know if this is still a folklore conjecture or someone has proven. Maybe Friedrich has insight on this thing. But if you have a generalized metric which is Ricci flat, then reduction of the current algebra should produce another Ricci flat metric. But you may have a divergence. So when you reduce, you may introduce a divergence. So the reduced metric may be generalized Ricci flat with respect to some divergence. So I wonder if your examples fit into this picture of generalized reduction, and I mean, whether some of the hypotheses that you're imposing are somehow killing the divergence in the reduced generalized Ricci flat metric, because you are reducing from a product of compact semisimple groups, which we know do have generalized Ricci flat metrics. Furthermore, they are bismuth flat. So this procedure by reduction should induce generalized Ricci flat metrics with divergence. So somehow you are killing this divergence to produce your examples. And then if this is the case, then the check of having the check of the reduced generalized metric being non-bismuth flat will just be a topological thing, right? You just need to check that the reduced manifold is not a Lie group itself, because otherwise it will be bismuth flat.
I see. Yeah, thanks for this. Yeah, I didn't know that reduction process. So I will check this. Thank you.
Fredrik, is this completely done in your papers or is still not clear?
Which part do you mean? Like the reduction of? I mean, reduction is compatible with the Ricci tensor. So if it was 0, then it should be 0 after reduction. That's true, I think. But yeah, I don't see this why the divergence would vanish. So I don't have an insight into that.
Yeah.
Just so I understand, Mario, you're suggesting that maybe these examples are just somehow generalized reductions of this standard flat metric on the product.
Yeah.
That's
this
interesting.
It looks like that. So which also tells you that probably there are much more examples, but without divergence, which is compatible with the divergence should be special, should be compatible with the generalized metric. So you should have a killing vector field, which furthermore, the contraction of the killing vector field with the 3 form is d of a 1,4. And this should also appear in this picture naturally. If it is the case, and then somehow your construction is pinning down the ones which have 0 divergence.
And so, which is the reference of Friedrich you were mentioning?
But probably Friedrich can say, but it's his papers with Chavera.
Uh-huh.
Okay.
Yeah, there is a paper which has supergravity in the title. That's how I find it usually.
I'll have a look.
Any other questions or comments? Well, yeah, if not, let's thank the speaker again for a nice talk.